Hello, in this video we'll continue with our discussion of the inference rules for predicate logic. So far we've introduced the rules of existential introduction and universal elimination. Now it's time to bring in the other two. Let's start with Universal Quantifier Introduction. To understand this rule, we have to do some stage setting first. In particular, we'll start by discussing the two main ingredients of the Universal Introduction rule, which are the notion of the arbitrary occurrence of a name and the operation of universal generalization. We'll start with the arbitrary occurrence of a name, which is itself built on the notion of government of sentences by premises and assumptions. Once we define the conditions under which a name occurs arbitrarily, we'll deal with the operation of universal generalization. And finally, with all the ingredients on the table, we'll finally state the universal introduction rule, followed by an example. Okay, get comfortable. Here we go. Universal introduction brings in a universal quantifier where there was none. Thus, it always involves drawing a universal conclusion from a non-universal premise. But how can you validly derive a universal conclusion if your premises are not themselves universal? To see the problem, consider constructing a derivation for this intuitively valid argument. Everything is both f and g, therefore everything is f. As always, let's write our intended conclusion on the right. Then we may derive fa and ga by universal elimination, and then get fa by ampersand elimination. And the last step would be to write every x is f from a is f. But this last step seems suspicious. Is it valid? Let's give an example of this pattern in English. This would be like saying Alice is fun, therefore everyone is fun. Yuck, this is definitely not good. This is an example of the fallacy of hasty generalization, where you reach a conclusion about a whole population from information about a single member or a few members. How can we introduce universal conclusions without falling into obvious fallacies then? Perhaps the notion of arbitrariness, which is often used in mathematics, can help us here. Suppose that you are in a geometry class, and your teacher starts a demonstration with the words, "Let ABC be any triangle." Then some mumbling and writing on the chalkboard happens, and in the end, the teacher turns around and exclaims, "The sum of ABC's interior angles is 180 degrees. However, he doesn't leave it at that. He immediately draws a much more ambitious conclusion, namely, for every triangle, the sum of its interior angles is 180 degrees. But how come, you may ask? All the scribbling and mumbling had to do with ABC. And so far he hasn't said a word about any other triangle. How does he get to extend his proof to other triangles? I mean, isn't this like saying Alice is fun, therefore everyone is fun? Well, not really. The key part here is the way in which ABC was introduced. By stipulation, ABC doesn't have any features that distinguish it from any other triangle. There's nothing special about ABC. The only thing we know about ABC is that it is a triangle. This lack of distinguishing properties allows ABC to be a proxy or stand-in for any triangle whatsoever. If instead the teacher has started by saying, "Let ABC be an equilateral triangle," for instance, then his proof would lose generality. And although it may apply to all equilaterals, you could doubt whether it applies to all triangles. Then let's go back to our initial problem. Suppose that A is just an arbitrary member of the domain, and that we make sure that A's only relevant feature is that it belongs to the set of things that are f and g. So A has no special properties that distinguish it from other members of that set. In that case, and given the premises, we can perform inferences on A and then generalize on the results, so we can introduce our universal conclusion. And indeed, we could have obtained exactly the same conclusions by using any other arbitrarily chosen name, such as B, for example, or C, or like K127. In our system, we indicate that an occurrence of a name is arbitrary by putting a silly hat on top of the letter. If you're familiar with French, you'll surely recognize this as the character for the circumflex accent, but here we're going to call it a hat. So the silly hats indicate that all of these are arbitrary occurrences of the name A. In this next section, we're going to give a set of conditions that implement this intuitive notion of arbitrariness in our formal system. These conditions are going to ensure that the use of a specific name is truly arbitrary at any given point in the derivation, and that it doesn't carry with it any sort of distinguishing characteristics or any kind of undesirable logical baggage. Moreover, these conditions merely have to do with where the name appears in the derivation. They're purely syntactic or formal. Okay, here's the definition of an arbitrary occurrence of a name in a derivation. I warn you, there's some terminology here that we haven't introduced yet, so we're going to have to do some work. We have all the elements we need to understand it. A name S occurs arbitrarily in a sentence X of a derivation if S doesn't occur in any of the sentences that govern X. The notion of government seems to be doing a lot of work here. So what is government? Government is a relation between two sentences, or rather between two occurrences of sentences in a derivation. So suppose a sentence X occurs in a derivation or subderivation. That occurrence of X is governed by a premise or assumption Y if and only if Y is a premise or assumption in X's derivation or in any outer derivation with respect to X's derivation. Moreover, any given premise or assumption governs itself. Here's an example. In this configuration, FA is governed by every X fx, because every X fx is a premise in FA's derivation. Again, in this longer derivation, FA is governed by every X fx. Every X fx also governs DB, and for the same reason. But DB is not governed by FA because FA is neither a premise nor an assumption. DB is governed by itself because it is an assumption in its subderivation. FC is governed by every X fx and DB. And there is an X, SIX or SBX is governed by every X fx and by DB. The sentence in line 6 is only governed by the sentence in line 1. It's not governed by DB because although DB is an assumption and occurs before line 6, it is not a premise of the derivation of line 6. You see, line 6 doesn't occur in the subderivation, since by the time we reach it, the subderivation is closed. So line 6 belongs to the outer derivation. And in the outer derivation, the only premise or assumption is every X is F. Hence, the sentence in line 6 is only governed by the premise in line 1. Okay, now that we understand government, it's time to revisit our rule for arbitrary occurrences of names. A name S occurs arbitrarily in a sentence X of a derivation if that occurrence of the sentence X is not governed in any derivation in which the name S occurs. So, according to our definition, A occurs arbitrarily in this derivation. That is because A is part of FA is only governed by every X fx, and the name A does not occur in every X fx. In other words, the name A doesn't occur in the sole sentence that governs FA. Let's consider this other situation. Here in line 2, B is arbitrary. It doesn't occur in every X LXA, which is the only sentence governing LBA. Furthermore, there are two occurrences of the name A, and neither of them is arbitrary. In line 2, every X LXA is a premise, so it governs itself. Therefore, A occurs in a sentence that is governed by another sentence that contains A. On line 2, LBA is governed by every X LXA, which is a premise. And again, A occurs in every X LXA. Finally, let's look at this derivation. A is arbitrary in line 2. B is not arbitrary in line 3, because it occurs in an assumption. C is arbitrary in line 4. B is not arbitrary in line 5, and this is because B occurs in DB, which governs there is an X SBX. A reminder of our notational convention. Arbitrary occurrences of a name will be written with a hat on top. So this is how we would notate that the name A in line 2 and the name C in line 4 occur arbitrarily, but the rest of the names do not. So a question for you. In this derivation, which occurrences of A are arbitrary? Here you have to ask for each of the occurrences of A, first, what derivation does it occur in? Is it a subderivation or is it an outer derivation? And second, is A governed by another occurrence of A in that derivation? Okay, think about it for a second. Only the occurrences in line 3 are arbitrary. The first occurrence in line 1 is part of an assumption, so it is self-governed, as it were. The two occurrences in the second line are part of the subderivation that began on line 1, so those occurrences of A are governed by the occurrence on line 1. However, by line 3, the subderivation is closed. And if FA, then FA or GA occurs in the outer subderivation, where there are no occurrences at all. Okay, now we can introduce the idea of a universal generalization on a name. This is basically the operation we perform on arbitrarily occurring names, so as to introduce a universal quantifier. This is the rule. The sentence every U is such that something and something U results by universally generalizing on the name S in a sentence containing S, if and only if one obtains the universal sentence from the one containing the name by, first, deleting all occurrences of the name S in its sentence, replacing each of those occurrences with a variable U, which is free at these occurrences, and applying the universal quantifier followed by the corresponding variable to the result. So suppose we want to universally generalize on the sentence FA. Then we first delete the name A, then we write the variable X in its place, and last we put a quantifier at the start. Now let's do the same with RAA. First, we delete all of the occurrences of A, which is the name we're going to generalize on. And in their place, you'll write two occurrences of the same variable. I chose Y for variety's sake. And finally, we stick a quantifier with the right variable at the beginning of the sentence. Now let's start from LAB, and we're going to generalize on the name B. Then we delete the occurrence of B and have X instead, and finish by prefixing a universal quantifier that's going to bind the variable we just introduced. But we can generalize further. Let's generalize on the resulting sentence, but this time with respect to the name A. So we delete A, and we introduce a different variable, Y in this case, because if we had chosen X, then the new occurrence of X wouldn't be free. Last, we place the corresponding quantifier at the very front. Okay, this is all for universal generalization. Now that we have all the necessary ingredients, it's time to formulate the universal introduction rule. The rule goes like this. If a sentence X occurs in a derivation, and at the place where it appears a name S occurs arbitrarily in X, then you're licensed to conclude anywhere below the sentence which results by universally generalizing on the name S in X. So the notion of arbitrary occurrence of a name demarcates the places where you can generalize. And universal generalization is an operation you can perform when you encounter an arbitrary occurrence of a name. Diagrammatically, if on line N you have a sentence in which the name S occurs arbitrarily, and at a later line you can write the universal generalization on name S, and you can justify the step by universal introduction on N. But remember, a universal generalization with respect to the name S must involve all the occurrences of S in the sentence. It also requires the occurrence of S to be arbitrary. That is, the name must have a hat. Now let's go back to the problem at the beginning. From everything is F and G derive everything is G. Here's premise 1. Then, as before, we get FA and GA by universal elimination. But notice that both of these occurrences of A are arbitrary, so we put a hat on top of each of them. Then we get FA by ampersand elimination. And this occurrence of A is also arbitrary, because although A occurs earlier on line 2 is neither a premise nor an assumption. Finally, since A occurs arbitrarily in FA, we can universally generalize on it, and we can write the result on line 4. The justification is universal introduction, line 3. Now it's time to do lots of exercises. Taylor's text has many. There's also a couple in the weekly assignments. Okay, that's all. Goodbye.